Hi, I am Engineer Febus Reidj Cruz from Mapua University, School of Electrical, Electronics, and Computer Engineering. I hope that you are having a wonderful day. In this video, you will be familiar with the generation of charge carriers, the effect of temperature on carrier density, and the transport of free electrons and holes in semiconductors. A charge carrier is a particle carrying an electrical charge and moving as an electrical current. In semiconductors like silicon, the charge carriers are free electrons and holes. When the valence electron absorbs energy equivalent to at least the energy gap, the valence electron escapes the parent atom, then becomes a free electron, and leaves a hole or vacancy in the valence orbit. This process of producing free electron and hole pair from a valence electron is named generation. The absorbed energy can be from temperature, light, radiation, or voltage. As the free electron travels, it uses kinetic energy, releasing heat, light, or radiation, depending on the semiconductor material. Silicon material dissipates heat, while gallium compound emits light, such as in light-emitting diode or LED. Eventually, the free electron loses the energy and falls back into a nearby hole in the valence shell and returns as a valence electron. This process of a free electron returning to a hole and turning back into a valence electron is termed recombination. The time of free electron existence from generation to recombination is called lifetime. High-speed semiconductive devices have shorter lifetime characteristics. The number of generated free electrons or holes in intrinsic semiconductor material depends on the energy gap of the material and the temperature. The N sub I of silicon equals 5.2 times 10 raised to 15 multiplied by T raised to 1.5 multiplied by the exponential of the quotient of negative E sub G and the product of 2, K, and T. The N sub I or Ni is the density or concentration of carriers per unit volume of silicon in carriers per cubic centimeter. T is the temperature of the material in Kelvin. Note that the temperature in Kelvin equals the temperature in Celsius plus 273. E sub G or Eg is the band gap energy. It is the energy gap between the energy level in the valence and the energy level at the free electron state or conduction state. The energy gap of silicon equals 1.12 electron volt, wherein 1 electron volt is equivalent to 1.6 times 10 raised to negative 19 joules. K is the Boltzmann constant, equal to 1.38 times 10 raised to negative 23 in joules per Kelvin. To illustrate the effect of temperature on carrier density in the silicon material, the carrier density is calculated at different temperatures. As the temperature increases, the carrier density increases exponentially. At room temperature, 27 Celsius or 300 Kelvin, the density of carriers in silicon is 1.08 times 10 raised to 10 carriers per cubic centimeter, or 10.78 billion carriers per cubic centimeter of silicon material. Here is an illustration of a silicon material with free electron and hole pair. A voltage is applied with positive polarity on the left side and a negative terminal on the right side. The free electron having a negative charge is attracted towards the positive terminal of the applied voltage. The transport of free electrons produces electron current. Now focus on the hole, the other type of semiconductor carrier, and see how it is transported in a silicon crystal. Again, the applied voltage has positive polarity on the left side and a negative terminal on the right side. The hole is defined as a vacancy in the valence orbit. The hole indicates an absence of valence electron. The hole cannot move independently since it is simply a vacant space in the valence. However, because of this vacant space, the nearby valence electron can occupy such space and move towards the positive voltage. Unlike when the valence is complete, there is no movement in the valence electrons. Now, at a time equal to T1, the valence electron is attracted towards the positive voltage at the left side and occupies the vacant space or hole. At a time equal to T2, the valence electron is transferred to the previous spot of the hole, and the hole is effectively transported towards the negative voltage on the right side. At a time equal to T3, another adjacent valence electron goes to the site of the hole towards the positive voltage. So, at a time equal to T4, the valence electron exchange places with the hole. Again, the hole is as if it is moving towards the negative voltage. Hence, the hole is characterized as a positive charge. The same goes at a time equal to T5. Another neighboring valence electron relocates in the space provided by the hole. As a result, the hole is transported towards the negative voltage. Note that the hole current is the flow of valence electrons along the valence shells moving from one atom to another atom. The transport of free electrons provides the electron current, while the transport of holes gives the hole current. Both electron current and hole current contribute to the current in a semiconductor material. When there is an applied voltage or electric field, the flow of carriers is called drift current. Drift current is the amount of current in response to the applied voltage or electric field. Aside from the drift current, there is another way to produce current in semiconductor. Even without voltage or electric field, the charge carriers in semiconductors move from regions of higher concentration towards the areas with lower concentration. This flow of carriers due to concentration gradient is the diffusion current. In summary, there are two kinds of charge carriers in semiconductors: free electrons and holes. The number of carriers in intrinsic semiconductors depends on the energy gap and the temperature. The transport of charge carriers produces the current in a semiconductor. The electron current is the flow of free electrons. On the other hand, the hole current is the flow of valence electrons moving along the valence shell, occupying the vacant spaces provided by the holes. These charge carriers move when an applied voltage yields the drift current. Also, even without voltage, these charge carriers travel whenever there is a concentration gradient, creating the diffusion current. Keep going with this series on basic physics of semiconductors. And before we end this video, please allow me to encourage you to appreciate your studies and enhance your creative and innovative ideas. Thank you and see you again in the next videos. Thank you very much.